From deep inside the Death Star, I'm Larry Larson.
And I'm Andrew Richards.
And welcome to Defrag Tools. Well, today we're talking about RAM maps. Thank you goes out to the Bing team for all the coordination that went into making sure that there's RAMs on the front page of Bing. So there's
coordination to the hilt.
Yeah. So what's the subject today? RAMMap, of course.
RAMMap. Another Sysinternals tool. It's the tool to work out what your physical memory is doing as opposed to an application's memory. And you use it to work out whether your system's under pressure. And so we've had episodes about boot log tracing, so you can work out, hey, I was saturated on disk. And we've had, last week was on auto run, so we can work out why do we even start that program. And then there's the next phase where you can go, well, was my system slow because it took a long time to bring the data in, or because it came in and then ran out of RAM and went out again? So RAMMap will tell you that. And so RAMMap's one of those things which have to know Windows internals. And there is two fantastic videos by Mark Rasinovich about this topic. It's called Mysteries of the Memory Management Revealed. They're 1.5 hour talks. And he goes through what physical memory is, and he goes through what virtual memory is. There's actually nothing to do with each other, but you need to know both concepts, because sometimes you look at something, you think, you've got to know which area it's in. So two-parter, back from, what was it, Tech Ed 2011, so last year's Tech Ed. Great videos, just if you want to truly understand what memory is, that's what it all comes down to. So what does RAMMap look like? Let's start this sucker. Standard EULA. Has to run elevated because it's going deep into the kernel. And it's just a lot of numbers.
Yeah.
Right? And so this is where you kind of have to go, well, what do all these numbers mean? I did a quick demo of this on a Defrag show thing, and we're going to go a little bit deeper today and go through what the numbers mean and what you can infer from the numbers, and what memory pressure there is. So across the top, we have all the different states that memory can be in. Now, this is about physical memory. Physical memory is it's fragmented by design. So if you have a program, and the best analogy I could think of this is that your program, say that it's Larry.exe and I have Andrew.exe, we have an equivalent of a brick wall. And every single brick in our space is nice and linear, and we tend to have it packed up nicely and tight. And you have a brick that's at the bottom left corner, and that'll be brick 0, and the next one will be 4K in. Everything in Windows is based on 4K pages of memory. And so you have 0, 4, and so on. And so will I. Mine will be called 0, 4. But we both can't have the same number in physical memory, right? We'd be contending. And so what happens is that virtual brick, that's at address 0, is actually translated into a physical brick somewhere. And more often than not, 048 will be in memory as 804. They'll be completely out of order. And it's completely irrelevant, because much like an SSD disk, it doesn't matter where you access memory, right?
The order doesn't matter. It's random access.
Exactly, right. And so it doesn't matter if you have fragmentation. The only issue you get with fragmentation is if a device driver needs to lock a big piece of physical memory to do what's called DMA transfers, which is between the physical hardware and memory, and it needs a big block, and storage drivers are the classic example of that. So you can have a program that's 2 gigabytes of RAM, right? A big, Adobe program or something, and I can have a big program that uses 4 gig of RAM, like SQL Server or something, and we both can share the machine. And collectively, we think we have 6 gigabytes between us. But the physical machine could have 512 megabytes of RAM. And you go, well, how does that work? How does that much 6 gig, we both know we have 6 gig and we haven't lost it, how does it actually stick into RAM? And that's where the page file comes into, and it's also where map files come into. So when you ask for a piece of memory, the operating system goes, all right, I have to move that into physical RAM. And that's what this column is all about, the active column. It's also known as working set. So your brick for the 4K in is put into physical RAM, or where did it come from? So if it wasn't in RAM, and in this case, let's say it's data that you're typing quick brown fox, that data came from the page file, right? And so the page file is a repository for blocks that didn't fit in RAM anymore.
Yeah.
If it was an executable, on the other hand, it would be paged in from larry.exe at a certain offset will be paged in. And actually, file copies are exactly like that. To do a file copy from larry.exe to larry2.exe, every single block is brought into active, which is the working set, and then that block of memory is copied back out to the disk into a different sector on the hard drive. Right? So you have this churn, and it's all about what's in active. That's the part that you can be used. All the other states of the memory are not accessible. They're purely an auditing journaling system, right? That's the memory that isn't usable by an application. If an application tries to use that, you get a page fault. Have you heard that term? So there's two types of page faults. There's soft page faults. So if the memory is in any of these blocks, anything that's not in the active, and it gets moved across to active, it's called a soft fault, and that happens in nanoseconds, right? So a soft hard fault is not bad. A hard page fault is when it came from the page file or a map file, which is like the executables or andrew.txt or something like that. They incur a hard drive hit, right? And so they're slow. And we roughly guess that it's 30,000 times slower to do that than to do a soft fault. So hard faults are bad.
Yeah.
And so one of the counters you can watch in your box is hard faults. The problem is you don't know whether the hard fault is backed by a memory file or the page file. You can't tell if your page file is being slammed because hard faults are just across anything that can be faulted in. So, all right, so here's what RAMMap gives you. It splits up the system into all these areas, and we'll go across first, then we'll go down, and then we'll go through the tabs.
Okay.
So across we have active, which is, as I said, the working set. Now, I just booted my machine. My machine has 8 gig of RAM, and currently only 1.7 gig is in active. The next one across is standby. Standby is where memory goes when you have something that's cacheable but no longer needed. So the classic example is I open up word.exe or winword.exe, use it for a while and close it. Instead of throwing all those bricks from Word away, which represent winword.exe and all the DLLs, we leave it in memory as, well, we have it pinned. If someone needs to reuse that memory, we'll just throw it away. But if someone wants to use that exact page from Word, we'll just do a soft fault, right, which is 30,000 times faster.
It's the off-ramp on the highway.
It's exactly right. So what we have is a state transition diagram. And I think it's viewable. So everything that is over here, this is the active area. That's actually what's usable. And as I said, the CPU will not let you address any memory block, physical memory block, that is in any of these other guys. So when you are using a program, you either use it as a read-only piece of memory or you may actually write to it, right? If it gets ejected from the working set because of pressure or age, it goes back to the standby list directly if, as this line down here, if it was just read-only, as in it wasn't modified. And there's physical hardware things that tell you whether a page is dirty or not, whether it has been modified. If it needs to be, if it's a rewrite page, like a piece of RAM that you're using the whole data, it will go to the modified list. And the modified list is, it's private data that needs to be persisted out to the page file, or it's a file that you have mapped into memory. So you don't actually have to pick up a file and put it into your own address space, like a read. You actually can say, grab this file and just shove it into my application as if it was RAM. And as you modify those pages, it will modify the file on disk. Much simpler access methodology. And so this can be either filled with pages that are going back to the page file or pages that are going back to a file on disk. Right? You have the modified page writer, which is a thread in the kernel, which slowly does it. It doesn't do it straight away. It does it it builds up the operations and then puts them out. That way your hard drive isn't continually churning. And then it finally gets to standby. So this could have been modified data got here or just straight read-only data. You want your standby to be full, right? You don't want these other lists to be full. It means you haven't used your RAM up. This is your cache. So currently on my box, I have 1.7 gig in active, 1.4 gig in standby, and I still have 5 more gig of RAM in the zero list, which we'll get to in a sec, which I've never touched since this PC is booted. That RAM is completely wasted.
Yeah.
All right. So what happens when something gets ejected? So if you stop a process, we don't want to keep that private data around anymore. There's no reason for it. Nobody can reuse it because it's private data, right? And so instead of going to the modify list or standby list, it moves across to the free list. So that's memory that no longer anybody can access that still has the data in it, right? So I could start a program, put a whole lot of data there, remember the address of where it was, and then close that program down. And then I can actually use a kernel debugger and actually look at that piece of memory still.
Nice.
Right? So memory dump files, if you shut everything down and then get a dump file of your machine, they're as dangerous as if the program was still running.
Yeah.
Right? It's still in the free list. So the free list, we don't, if there's spare CPU power, and there's a thing called the zero-page thread. This is the lowest priority thread in the entirety of Windows. It's priority 0. It's actually lower than the idle thread that makes the machine go to sleep, which is level 1. What it does is it reads the 4K pages, puts zeros all over them, and then puts it in the 0 list. We need the 0 list because when someone goes, I want to allocate some memory, I have to give it to you with zeros on it. I don't want my program to see your old stale data. That's a privacy concern, right?
Yeah.
And so it comes from there. So every time you go, give me some memory, it will come from the 0 list. If the 0 list is empty, it will get it from the free list, and the memory manager will write zeros over it. There's one optimization which is actually quite clever. If you are reading from the disk, we know that we're going to read a 4K block off disk and put it into memory. So we don't zero it out first because it's pointless. We know we're going to wipe it. And so when you pull in memory from a file, it pulls it from the free page list instead of the 0 list as an optimization.
Nice.
And then the last one is batch page. So if you have a physically bad piece of RAM, either at boot, you can set this through BCD edit options. You can set the BIOS can tell us through ACPI, and also you can actually hard code it in the registry if you have a dud address. Those bad pages will never be used.
So if you do find that you have some bad parts of your RAM, do you need to replace it, or are you good just having a little bit less RAM?
It's up to you. I mean, if a stick's going bad, do you trust the rest of it not to go bad? The memory diagnostic subsystem in Windows, the check memory at the start, this is what fills this in. What you can do is we can identify the stick.
Yeah.
Right, and that's how I'll show you that. That's probably what I'll do. I'd probably replace that one stick rather than run the risk of, I don't know. I don't know, but if I have a hard drive that's got bad sectors on it, I'm not trusting that much longer.
Yeah.
Right. And with RAM, it's so important. And then all you need is a single bit flip. And when we see this in support, that you go, there's no other explanation that a single bit on a single byte of RAM is just not toggling between 0 and 1 properly anymore. Right? Once you get single bit errors, your box is, it's blue screen of death fodder. Right? It's going to go down. So memory theory, I know, a bit boring and all, but this is what it all comes down to. General gist is, if you have it in working set, that's awesome. If it's in standby, that's pretty good too, because it doesn't actually cost you anything. If your standby is full and using all your RAM, that is awesome. With a caveat, which we'll get to. And then free list should relatively be empty because there should be enough CPU power in your box left over to turn it into 0. So if you have a lot of free, that's a bit concerning because it means your machine's a bit pegged. And then bad list is just bad hardware. So looking at my machine, as I said, I have 1.7 gig of, this doesn't refresh, by the way. You have to press F5 to refresh. 1.7 gig of active, fine. 1.4 gig of standby, that's a fair bit. So my machine's up to about 3 gig of either files or data, mainly files because there's not much data involved with booting Windows. 53 meg to be written out at that point in time. This is modified no write. So if the page is associated with particularly NTFS, NTFS wants to be transactionally complete and be determinant when it writes its main, what's called the MFT records, which is like the log file for NTFS. So it controls when it writes to disk. It doesn't want the modifier writer to do it at indeterminate times. And so those pages are marked as that. That's what that one is. Transition is moving between 2 states. So there was 2 of them that were 2 blocks, as I said, they're 4K each, that were moving between one of these states at this point in time. You also get that when it's getting created in the first place. And then I have 5 gig of zeros, not surprising, and 12 meg of free. So this guy, these 12 meg haven't had a chance to be flushed out to zeros, and then yay, I don't have any bad. So looking down the other way, this is how you split up all the reasons memory gets allocated. And some of these things are operating systems, and some of these are to do with processors. Process private, that's straight programs allocating memory. That's the system commit limit number. So currently I have 617 megabytes of memory allocated by programs in my total, and most of that is in working set, which is kind of cool. You'll see that it will slowly age out. So it will move out of working set because of age if you haven't touched it, put it out to the page file, and then bring it back into working set. At any time in that whole graph of arrows that someone needs it, instantaneously it will jump back to a working set to active. So it's not a bad thing that you're paging your stuff out slowly. So what is good is that when you take a dump file, or transactionally, you got more written out to disk already, so it happens faster. Map files, that's executables. So currently I have 1.5 gig of exes and 1.4 of them. So 100 something meg is in RAM, in active. The rest of it is in standby. So it looks like from me, just a quick glance, that this machine has read 1.5 gig of files off the disk since boot.
Yeah.
And most of it's been cached. Shareable is memory that we can share between each other. So you can allocate a block of RAM, and I can say, I want to access that block of RAM, and if you write to it in your program, I will see it in my program. And we use that as a communication mechanism. Programs use that. Page table entries, that is the memory to explain how memory is laid out. So it's the cost of explaining how memory is. Page pool. So these two, page pool and non-page pool, are the ones that are a bit, can be of concern, particularly in 32-bit OSs. There is a limited amount of page pool and non-page pool in those OSs. Page pool is memory that can be paged out, so it can go via the modified list and mount to standby. Non-page pool can't be. It means it's non-pageable. By definition, it must only ever exist in working set. If those numbers get big, it means you have a driver leak, right? And a driver memory leak, a device driver's memory leak is fatal to Windows. You'll finally get to the point where it just dies. So if you have big numbers there, that's a concern.
And what's a big number? At what point should you be concerned?
On a 64-bit OS, I wouldn't want to see those numbers above half a gig.
Yeah.
Yeah. On x86, because of the reduced memory space, around 100 megabytes each.
Yeah.
And after that, you will die. It will die at like 130 meg on most boxes. But yeah, in 64-bit world, because of the addressing, there is actually no limit. It'll let you have terabytes, but you will run out of memory. And as I said, non-page pool can't be paged out. So once my machine has 8 gig, once that gets to 8 gig, this box is hosed.
Yeah.
Right. System PTUs is how you explain memory in the kernel. Session private. So in a terminal server sessions or fast user switching, we get a session each. Like you get your own Windows desktop, I get my own remote desktop as well. So this is memory that's associated with per session private. So it's kind of like a process private in that way. It just happens to be allocated for that reason. Metafile, this is the overhead to do file caching. If this number is big, you have hit a file caching bug in Windows. Right, and you need to go look for a hot fix. They do come around every once in a while. I've seen a couple of support cases, but we do patch those and put them out as Windows updates. But if you're seeing a high metafile number, it probably means you're missing an update. AWE, you don't really use that much on 64-bit, but you do on 32-bit. That's actually how SQL Server used to access more than 4 gig of RAM back in the 32-bit Windows days. And so it actually carves out the physical memory and actually makes it inaccessible. So that part of memory isn't actually available for normal working set reasons, which everybody else can use. Driver locked. This is a very interesting one. So have you ever thought about how Hyper-V works?
Sometimes at night when I
want to go to sleep.
Yeah.
So you have this machine, right, with say 64 gig of RAM, and you say, okay, just give this nice Windows 8 VM 8 gig of RAM, so it runs nice.
Yeah.
Well, how does the physical memory of my box turn into the physical memory of that other box with its own memory manager that's dealing with it its own way? And the way it does it is the Hyper-V device drivers on the host, on the server, say, give me a big block of memory, Mr. Memory Manager. Give me this nice 8 gig range, and it's linear as well. And it says, do not use it anymore. That's mine. I'm locking it, right? And it completely takes it out of the whole memory availability. And then what happens when in the guest, it's told your memory starts at this offset. This is your memory bank. And then you can go control that memory as any way that you wish. So that's how hypervisors give out memory to boxes. The other way it's used by VMware is VMware ballooning. You ever heard of that term?
Yes.
So that's the thing that lets VMs, you overcommit the memory. And what the device driver in the guest does is it actually driver locks a portion that they want to de-balloon, maybe that's the word for it, and they steal that memory back.
Inflate.
And inflate, yeah. And they inflate that balloon and it makes pressure on the box.
Yeah.
And the remaining pages is what you use. And because they know that those pages are now empty or unused, they actually go and reuse them in another guest, right? And so if you see a high driver locked in the host, that's awesome because it means your VMware's or your Hyper-V is working great.
Yeah.
If you see it in a guest, it means that a ballooning technology is happening. Kernel stacks is just the stacks used by threads. Kernel stacks are actually tiny. You get 1 megabyte in user space, but you only get 4K in kernel, so you shouldn't have too much of that. Unused, yeah, I said that's just how much I have free. I have 5 gig. That's a total of 0 and free at the moment. And then large page allocations, which is how you do. Sometimes just making lots and lots of 4K pages is not optimal, so you can say to the memory manager, give me a big block, and I'm going to use this big block for my reason, and that where you don't have to incur the cost of remembering all these little 4K things. So, yeah, across the board, lots of numbers, right? And you can. I'm not going to go to the menu today. You can file save as XML, all that stuff. So let's have a look at what this sucker can do, right? How it can drill into your box and give you some information. So here is all the programs running, and the weird thing about this is you actually can pick up zombies. You go, what's a zombie, right? So a process exists because it's reference counted, right?
Yeah.
A process has a thread in it, and then there's pointers around that keep everything alive. And then when the process dies, when the last thread dies in the process, it decrements its count by 1. Process should get down to 0 and then disappear. Well, you actually can have these processes that still exist that don't have any threads anymore, and that's called a zombie process.
How often does that happen?
Unfortunately, more than we would like. It's a mistake. So what's happened is a device driver along the way has taken a ref count out on the process as it's looked at it, and then didn't deref it. It made a mistake. And so as soon as the count's greater than 0, and on these you tend to see zombies with big numbers, they stay there and they pin all the memory. Right, and so this thing never dies.
So what does that look like to the user?
Just memory contention. You're going, well, what this actually will show you, your memory usage will be high, but you'll look at your programs and go, I'm not using much here. It doesn't make sense. So every tool, Process Explorer, Performance Monitor, everything, Task Manager, none of these guys will see a zombie, right? And so if you see like 12 in the Process Explorer list, or 25 to be realistic, and you see hundreds in here, and it'll probably be, or maybe the same, actually may not be. But if you see way more in here, you know you've got zombies.
Yeah.
The other way of doing it is you can crash your box, get a memory dump, and do it the hard way. But this lets you see it real time. So if you've got issues with memory just being used up and you can't explain why, look for zombies in here, and you can just look for process IDs that don't exist in Process Explorer, for example. This is per process, so you can see that RAMMap itself is using 51 megabytes of private memory, 304 megabytes of page tables, and you can just see how everything's cut up and diced. It's just pure stats. So the biggest user of memory on this box is this SVC host. Prioritization. So on the memory graph over here in Process Explorer, you'll see all these priorities. And so when you allocate memory, and so what you're seeing here, this list here, is exactly the same list as we're looking at RAMMap. Right? It's the same data. When you allocate memory, you say what prioritization it has. And so the lower the number, like 0, means it will be sacrificed sooner than other things, right? And so everything will get, as it goes, numbers get higher and higher, you would hope there's not too much, you don't want too much memory who thinks it's, ultra high priority.
Yeah.
Then it kind of defeats itself. The repurpose column is probably about the only tool and this is probably the only tool I know that actually can tell you whether you have memory pressure or not. So memory goes from active to standby. And let's say that you've used up all your memory on your box. And actually, I'll open up a RAMMap file which shows you this. And everything's full, 0 is empty, and free is empty. Well, memory has to be, if someone asks for more memory, standby is ejected, right, and repurposed for that reason. So that's what this column is. It's how much memory has ever been repurposed for that priority. Obviously, priorities 1, 2, 3, 4, they're lower in the stack, so you expect them to get reused, right?
Yeah.
If you see 4, 5, 6, 7 get repurposed, it means this ultra high priority memory that should never be ejected, there was so much memory pressure that those things got pushed out, and that's not a good thing.
Yeah.
So I'll open up another file. Where is it? And I actually have my machine from work that I've had, and this guy's been running for weeks, right? And I've been opening hundreds of gigabytes. Now this guy has 16 gig of RAM, and he's opened up gigs and gigs and gigs and gigs of data. And as you can see on this guy, the standby list at the bottom has the counts are like 16 gig of RAM, 5 gig in working set, and 10 gig in standby, and 0 and free are relatively empty.
Yeah.
Right. So this guy is using his RAM, and the prioritization shows you that only the low priority stuff got ejected, and the high priority stuff didn't. And that's the good thing, right? So you expect to have the reuse at the bottom.
Yeah.
As I said, if you see the big numbers at the bottom, that's really bad, and it's probably the only clear indication that I know of that tells you you should go get more RAM.
Yeah.
Simple as that. There's nothing really else that can be that definitive. Physical pages, as I said, every single page is a 4K, so you'll see a 4K increment. It tells you what every single one of those bricks, real bricks in memory, is currently doing. So that brick has been used for non-page pull. That's been used for non-page pull. This has been used for driver locked. And what you can do is sort by some of these. Now, the one that you worry about is the non-page pull and the page pull ones. Those ones actually have names. You can actually give them a little name. And so what we can say is, show me how much memory this guy has. And he's only got 1 block, 3 blocks. And you can sort it. And so you can actually work out, well, I know that the CCVA tag through Binging and various other reasons is associated with this driver, and then I have a big leak. And so you can say, well, I have a lot of page pull, let's work out what it is, drill into it, and then using the physical pages, you can actually work out what physical page of memory it is, and then who's using that page and how much it's using. So you can do a lot of statistical stuff. Physical ranges, so this is the actual way that the memory sticks are represented in the box. Right, and so you'll see there's some fragmentation, and that's just caused by the way that PCI has pushed pages around. So the memory sticks don't necessarily get a linear address space because PCI takes ranges out for its own use, and so the memory is reshuffled around. Simple as that. And usually, like I've got 16 1 gig sticks, I believe, in my server for my desktop, and as you can see, they've been all pushed around. File summary. Now this is probably one of the coolest things. Now I'm going to just for actually I'm going to do an F5. I'm actually going to get my own personal data off this box because it's a better example. So currently, here's the RAMMap file I just opened. Right, there was 213 megabytes of it. So I opened up a file and then I pressed F5, which gave me my live one again.
Yeah.
So that file just got ejected from memory. It's currently in standby, right? It didn't get lost. And so if I open that file again, I will not even touch the hard drive.
Yeah.
It'll come straight back in. So you can work out what's in your cache. So I've been looking at RAMMap files. I copied around my hard drive a bit. There's a whole lot of Windows stuff, and we can, you can go through here and work out what's what. These ones are currently, these ones which have active on them are in memory at the moment, right? So they're probably being used. For a file, you then can go actually a little bit further, and for example, this guy, we can work out the physical address where it is, which list it's in. This is for every single block in that file. The map file, how it's mapped in, so if it's map file, a page file, or whatever. The memory priority, so some of these pages are 2, some of these are 5. This one's in the image, this one isn't in the image, even though it's exe backed. And then the offset to the file itself. So there's no, see how we're looking linearly down the physical address range?
Yeah.
Yeah, the offset is all over the place. As I said, the bricks don't line up. And it doesn't matter that they don't line up. And what you can do is, you can save these off and do finds for presses and stuff. What you can do is use RAMMap as a testing tool, right? So if you run a program, all these things have to get paged in, all these XEs and DLLs. And so the next time you run the testing tool, well, there's no hard faults. You don't have to pull that 1 gig of XEs off the hard drive and wait 30 seconds for it. It will be there instantaneously. So it makes it look like you're running faster than you are.
Yeah.
And so when you have test runs, what you can do is you can eject all these. So you can say eject the working set, which is the active column. You can eject the system working set, all these ones, and you can eject all of these. And roughly what that does is it just pushes everything out of RAM and makes it empty again. And so every time you do a test run, you'll get the same amount of hard folding in, and you'll get the same load time. And so you get a nice, consistent test run. So if you're doing performance metrics on your application, the other mistake people make is, they debug on their application, they compile it, and they run, and they go, oh, it's fine. Well, that's not indicative of what a customer has to do. A customer hasn't got it in RAM yet.
Yeah,
right?
yeah.
It's not real. So when they say it works fine on my box, well, that's why. And that's about it for RAMMap. RAMMap's a great tool. You can automate it on the command line and blah, blah, blah. Once again, it's in the book. Actually, I couldn't find it last night. I actually had to ask Mark what chapter it was, because I was looking somewhere completely different, but it's hidden way at the back in chapter 14.
Yeah.
I was looking for it in the process area of the book. Once again, great book. I've noticed that Amazon's bumped up the price. It was like
Really?
$26, it's up to 30 now.
It's because of your promotion.
Yeah, it's too popular.
Yeah.
They're trying to...
Oh, well, it'll come back down.
It'll come back down.
We'll tell you when it's on sale.
So that's RAMMap. RAMMap is a great tool for just understanding what your physical memory is about. Next week, we're going to move on to VMAP. It's brother, it's sister. This is about physical memory. The other tool is about virtual memory. I highly, highly suggest that you go watch the Mysteries of Memory Management Revealed videos.
Yeah.
Fantastic videos. I can't do justice for like a half an hour on memory management. You do need to go look at 3 hours of videos by the master Mark.
Yeah.
But great tool just to work out what your machine's doing. Is it pegged? If it's not, you want to see standby high, but you don't want to see it repurposed. And that's the goal for the day. So.
Cool.
Yeah.
So that's the show for this week. If you want to leave us comments in the show, we can respond to you there, or you can email us at defragtools@microsoft.com. Love to get questions, so send them on, and we will see you next week.
Have a good week.